John again for accepting to give a talk on digital twins. So I will give a short introduction of you. So Professor John Erkoyuncu is a professor of digital engineering and head of the Center for Digital and Design Engineering at Cranfield University in UK. His research interests are quite large, but it includes digital twins, augmented reality, and digitalization in the context of true life engineering. He has an important track record in leading cross technology readiness levels in his research in manufacturing digitalization, with over 12 million pounds of funding secured from EPSRC, which is the Research Council of UK, Innovate UK, AMSCI, and KTP. Professor Erkoyuncu published over 150 journal and conference papers, and he's currently co-supervising 9 PhD projects, 7 of which are co-founded by industries. He has supervised over 100 master student projects. John is a co-chair of the True Life Engineering Services Council, member of the Team Defense Information, Digital Twin Working Group, council member of Digital Twin Hub, that I think many of you already know, and chartered engineer with IET. He's also fellow of the Higher Education Association and an associate member of the International Academy of Production Engineering, CIRB. And he was the former chair of this academy regarding research affiliates. And he is also the program director of, I think, an important Master of Science program in Cranfield and UK, which is related to digital and technology solutions. So with this, I will give Professor John Erkoyuncu the screen to present an interesting talk on the past, present, and the future for digital twins.
Great. Thank you, Nabil. Thank you very much for that bio. Good afternoon, everyone. It's a pleasure to be here today. So what I'd like to do in this presentation today is really to give you a bit of a feeling as to how digital twins are evolving and how can we start to maybe visualize where digital twins can be used in the future. So with that, I think I'll just proceed. In this presentation, I'll talk about what is a digital twin. I'll give you some examples where digital twins have been built. I'll try to go into some details on the particular use cases and really try to discuss what sort of benefits we can get from digital twins. So the concept, and I'm referring here not necessarily to the technology, but the concept has actually been around for quite some time. So you can see in this slide, NASA developed the Apollo program, and what you can see here is on the left-hand side, you've got the astronauts. In the middle, you've got a physical representation of the Apollo. And what this is trying to do is it's listening to what the astronauts were doing, what sort of changes they were making in the asset, and they were trying to replicate that in this physical simulator. So that was done manually, and they were trying to understand through this physical simulator what kind of problems could be experienced in the future. So very much trying to be proactive and understand how they can make better decisions moving into the future. So like looking at the image on the right-hand side, they were trying to predict severe damages, and they were trying to prevent these by giving feedback back to the astronauts so that they could change the way maybe the way the Apollo was being used. They could start to make modifications also in terms of the way they were maintaining it. So the idea for the digital twin is very much trying to create this representation of a complex system so that you can start to maybe manage that asset better over time. So there is some ISO standard developments, and this is one version from 2021 where they define digital twin as fit for purpose digital representation of an observable manufacturing element that's synchronized between the element and its digital representation. So the word synchronization is a relatively key word there, but there are many definitions out there, and it is quite a confusing concept. And I think in this presentation I'll try to give some further explanations as to what's unique, what's different with digital twins. So I guess here a core aspect related to digital twins is the fact that you're exchanging data. This is a key thing here. You're exchanging data from the physical object, which is the circle on the left-hand side, and you're collecting data, whether it's live or not, you could debate it, but that data is feeding into a virtual object. And that virtual object is where you're doing some kind of simulation, maybe some kind of optimization. And the results from that is feeding into the physical object. And this two-way communication represents the digital twin. So we're trying to have some kind of improvement. That's the key thing. You're trying to get some value out of the system, and you're trying to improve that value over time. And you can define value in different ways. One definition could be in terms of how you measure the availability of the asset. One measure could be in terms of the outputs that you're getting from the system. So there's different ways you can define value. It depends on the asset. It depends on what you're trying to achieve. But ultimately, you're trying to improve the value that you're getting over time. So that's the role of the digital twin. So the definition that NASA created in 2012, and again, this is just to illustrate where we are coming from. A digital twin is an integrated multi-physics, multi-scale simulation of a vehicle or system that uses the best available physical models, sensor updates, fleet history to mirror the life of its corresponding flying twin. So data exchange is at the heart of this. The ability to integrate data from different places is at the heart of this. There's different types of data that you're integrating. And it's very much to have a holistic understanding of the system of interest. So this slide is trying to maybe show the evolution of digital thinking, let's say. So if you look at the left-hand side where it says digital model, the dotted lines are showing that there is no direct connection between the physical object and the virtual object. So in this kind of context, maybe you've built some kind of CAD model, and that is not being updated through any live data that you might have from the physical asset. So over time, the model, the virtual object, and the physical object may deviate over time because you're going to make changes in the asset and things will evolve in the asset. And you're not necessarily feeding that back into the physical object. So as an outcome, the model's representativeness over time may actually reduce. If we move to the middle scenario, digital shadow, so in that context, there's some sensors on the physical object, and we're able to collect some data into the virtual object. So the virtual object is where we've got some optimization, some simulation, and those are being updated based on the new data that's coming in that we're capturing through sensors or different ways of data being collected. But the important thing here is you've got some way of collecting data and you're feeding that into your virtual object. So, so that virtual object is creating some optimization, some maybe suggestions. But in this context, there's no direct feedback back into the physical object. So just to give an example, maybe you could consider condition-based maintenance, where we're collecting the data, but we don't necessarily act on the optimization results. It's an option. It's kind of potentially we may use that, but potentially we won't use it. Now, if I move to the right-hand side, focusing on digital twins, the key thing there is there's two-way communication. So the physical and virtual object are communicating with each other. So the sensing data, the various information that represents the health of the object is feeding into the virtual object. We're coming up with some kind of optimization, and that's feeding back into the physical object. So we have some kind of control systems that are interacting with the virtual object, and we're able to modify potentially the way the asset's being operated, or potentially in terms of how the asset's maintaining itself as well. So that could also be the feedback that we're providing. Now, a key sort of maybe clarification I'd like to make is the orange line, you can see the arrow going from left to right. It's not trying to highlight that every decision-making approach is going to become digital twin based. I think the key thing to recognize is we have different types of decisions that we're trying to make. And some are suitable in terms of a model. Like an example could be spares models, where you're trying to predict how many spare parts are needed. We'll need a modeling, digital model approach. We'll need a digital shadow approach, and we'll also need a digital twin-based approach. I think the key thing is to decide where will you get good value out of these different approaches, and what is critical. What is going to be the absolute minimum value that you're trying to create? I think that will have a big role in terms of choosing which approach you're going to take. And I think the other thing to consider here is the amount of effort that's needed to create these things. As you move from a model to a twin, typically the effort needed is going to increase. So how long it takes you to build this, you need to consider that as well, depending on the value creation opportunities. So we at Cranfield, we worked on a step-by-step process to create digital twins. And we published that in this paper. So I think, I'll give you some examples as to how we applied these steps and created some digital twin examples in the next slides. But just to give you an overview here, we have defined 8 steps to be able to create a digital twin. The first step really says, what are the requirements? How do we start to illustrate what benefits we're trying to get from a digital twin? How do we characterize whether a digital twin will actually be needed? And what level of constraints will there be? What types of constraints will there be? And how will they drive the way the digital twin could work? Step 2 looks at the information flow. So the question there is, what data can we collect? How do we collect this? How do we store this? And how do we actually build an interface between the data and the model, so that we've got a consistent flow of the data? Step 3 is focusing on how do we communicate with different types of stakeholders. So there's different maybe needs that different people have. There's different kinds of information they're interested in. What's the best way to share that? So just to give an example, let's say I'm a maintainer, I'm working closely with an asset, and I need access at the point where I'm engaging with the asset. So I may not have access to a, let's say, computer screen. Maybe it's a different type of means to share information. Whereas if I'm maybe a project manager and I do have screens or access to different computers, in that sort of context, the type of visualization or data that I'm going to be presented will vary. And then if we look at step 4, this is where we're thinking about cybersecurity. We're thinking about how we're facilitating communication over time. How do we sustain this information flow? Because in some environments, there will be limitations as to what data can be shared and what methods can be used to share. So again, you need to think about those barriers and think about what's feasible. In step 5 is where we're doing the analytics. So it's very much about how do we come up with the improvement suggestions. So it's involving the different analysis. It's contextual. I think that's an important thing. And you're trying to optimize different requirements that you have in terms of the value creation for that asset. Step 6 is really saying the so what question. Like, what do we do if the optimization says we're underperforming, or there's an optimization which says the asset will fail before the date that we're planning for the maintenance. So step 6 is creating that feedback mechanism, trying to say, how do we change the asset's performance? How do we actually maybe put some limits as to how the asset will work? So step 6 provides that feedback mechanism. And then step 7 and 8 is very much focused on verification and validation. So we have to ensure that the digital twin system is working. And in some cases, the digital twin might deviate in terms of how it's representing the complex system. But ultimately, we have to find ways to become resilient with the digital twin. It has to sustain its representativeness over time. So these are the 8 steps that we have proposed. And I'll show you now some examples as to how we've created some demonstrations. So I'll come back to this in a moment in terms of the digital twin architecture. I'll just start with this example. So hopefully you can see this video. So this is a facility that has many compressors. So the question that we had given by industry was, how do we manage these compressors better using a digital twin? So the challenge that they had was they weren't aware of the health of the compressors to begin with. And secondly, when there were issues with the compressors, they were inefficient in responding to maintain them or repair them. So the approach we took here was we built a digital twin for the compressors for this facility, where initially we could identify the health of these compressors, and then we could characterize different types of problems that could be faced in the compressors. So this way, the system could give us some alerts before a problem is to happen. And when those alerts happen, we could give specific bespoke guidance to the maintainers that's created through the digital twin to do particular maintenance activities on the compressor. So the key thing here is the kind of interventions are not predefined. Depending on the health of the asset, depending on the type of problem that's faced, we could create specific guidance that the maintainers could work on. So that was the digital twin example that we created. And it led to significant improvements in terms of the performance of the compressors, but also in terms of reducing failures and reducing downtime as an outcome. So just to maybe go into a bit more detail in terms of how did we do that. So we created a data infrastructure. And that data infrastructure relies on the physical asset. It relies on the sensors that give us the data that we need. And we also created a database. So this, in this example, used MindSphere. And the data infrastructure, which sits right in the middle between the physical context and the digital context, it's trying to channel the communication between the physical and the digital environment. So we manage data collection through Raspberry Pi. We looked at the data storage through MongoDB. The data structure was managed through Protege using ontologies. And we looked at data control aggregation through simulation methods, visualization methods, and we came up with some actions recommendations from that perspective. We managed data flows through Python, and we looked at data analysis using Excel. So the key thing here was, how do we manage interoperability between all of these different software that traditionally may not have been designed to communicate with each other? So that was a big sort of challenge that we had to deal with. So just to go to another example. So this is using a gearbox as an example. So in this context, what we wanted to do was, how does the digital twin actually evolve over time? So you can see in this context, we have the gears. The gears are changing potentially. If one gear breaks, we have to replace it, and the new gear might have some differences from the original gear. So how does the digital twin cope with those kind of deviations? That was what we were interested in. And in this example, we're able to capture visually the changes in the gears. And we're also trying to realize how the performance of these gears are performing over time. And we're trying to optimize feedback back into the gearbox. Like, the key thing there is, how do we sustain the life cycle? How do we start to get the performance levels that we want? And the digital twin is giving feedback back into the gears to ensure that we are able to sustain those targets. Here's another example. So the kind of question here we were asking was, how do we build federated digital twins? And this concept is about having more than one digital twin. How do we start to have these different digital twins communicating with each other? And the example we've used here is small mobile cars. And we're trying to here illustrate that each car is a digital twin in its own right. And what we're trying to simulate is that, imagine a city where there's many autonomous cars. Now, in that context, how do we optimize the battery life of all these different cars? And how do we start to give feedback in terms of where can they charge the cars and what would be the best timing to charge the cars? So, so I think what you'll see in this video is that the car in its own right is a digital twin. It's able to determine where is the best place to charge, and where it's just crashed is the charging point. But what we can do is now optimize the route and do this with many cars. So I think the concept of federated is very interesting and very much crucial, as then in that context, we can start to deal with much more complex questions. And as we move that complexity, the value that we can get from digital twins will increase. So that's, again, a critical sort of consideration, because we need to think about value. Ultimately, when you're choosing the use case, when you're choosing where a digital twin should be used, the value you're creating is going to be a primary driver. So I'd like to just introduce this concept. So we have a PhD running on this at the moment, where we're trying to consider, what does resilience of a digital twin mean? And the way we define this is that in some cases, the digital twin will not receive the data that it needs. So maybe the sensor stops working, or maybe there's some kind of glitch in the data sharing processes. So if you look at this figure, you can see the red dotted line. So if we consider that there's a disruption, so this blue dotted line is where a disruption has taken place. And as an outcome, the accuracy of the digital twin is affected. So the blue line you can see is illustrating how the accuracy or the representativeness of the digital twin is changing. So if we look at the red dotted line, this is saying we actually take no actions. We leave the digital twin to function as it is. In that context, the accuracy will continue to decrease. The green line is showing here that potentially we've detected this, but we're delayed in detecting this. And that has led to some level of decrease in the accuracy. But with some time, that accuracy is improved. So this is just trying to say resilience in the context of digital twin is an important concept, because we cannot guarantee that the digital twin will be accurate and it will continuously represent the asset comprehensively. We can't guarantee that over time. So that's why we need to think about, how can we respond? How can we react to different kind of scenarios? So yeah, this is an ongoing PhD that we're working on. And here's an illustration of the PhD work. So if you can see, we have a ball at the top of this robotic system, and we're trying to ensure that if, for example, any of these legs stop working, how do we ensure that this ball is going to stay balanced at the top of this? So the digital twin is here to realize if there's any anomaly in terms of the performance of these legs. And the digital twin is trying to realize if there is a problem, how does it self-adapt? And you can see we've just removed the cable. One of the legs have stopped working, but the other legs have taken on additional pressure. And that's how the digital twin has reacted, has responded to ensure that the ball doesn't fall off this system. So it's a digital twin illustration, and it's demonstrating how we can have resilience in the digital twin. We've also been looking at wind turbines. I think the interesting thing about wind turbines is that the weather conditions are very dynamic. And you can see in this example, I'll just pause. We're trying to see how the wind is adjusting the wind turbine. So the kind of project is in terms of how the digital twin can realize if our sensing, so traditionally, like, there'll be some sensors trying to guide the wind turbine in terms of how we will optimize the energy production. So your misalignment causes inefficiencies in terms of the energy production. So if the sensor that helps with determining the alignment, your alignment, if there's a problem with the sensor, in that context, then we're going to have suboptimal energy production. So for us, what we did here was the digital twin realizes if the sensor has stopped working. And by realizing that, it's able to start to predict. And that's what it's trying to do, really predict the different maybe wind conditions and give feedback in terms of what's the best position for the turbines. So again, a very useful, let's say, industry relevant demonstrator where digital twins are helping to optimize energy production. And I think just to explain a concept around the federation linked to wind turbines. So we've been working on how can digital twins in different contexts, how can they actually connect, learn from each other, and improve their predictability. So what you can see in this slide is that we have a wind turbine, we also have a power plant. So in this example, we've created TLO, which is top-level ontology. We've built the ontology architecture to represent gearbox and generator. And given that a wind turbine and a power plant both have gearboxes and a generator, we can now start to learn from different applications, different uses of gearboxes and generators, and we can start to predict maybe future conditions and transfer that learning between the use cases. Now, the value of that is in terms of understanding different scenarios, trying to see what kind of behaviors were experienced in those different scenarios, and how can we maybe transfer that learning across different contexts. So even though wind turbine, power plant appears like they're very different systems, but there is some commonality, and we can learn from these commonalities. And the digital twin is whereby it's representing the approach that you can take to be able to build the connections. So having a digital twin for the wind turbine, having a digital twin for the power plant actually helps us to be able to connect these digital twins. So these connections between the twins actually help us to create federation. So if you scale this up, let's say to a nation where we've got many wind turbines, we've got many power plants, you can really see that the potential to improve predictability, the potential to understand these systems could be improved significantly. And I guess there's another big opportunity in terms of how do we actually integrate across the supply chains? And I think the other exciting concept here is how do we integrate across the supply chain and across the life cycle? So, so if I look at the suppliers are producing raw material, they're producing different types of maybe components that's feeding into the manufacturer. And if we had a digital twin of the suppliers, we could start to see what happens if we've got some delays. How does that affect the operations in the factory? If we had a digital twin of the factory, we could start to connect that to our warehouses so that we've got a better idea of what we need to store, when we need to store. And then once we have the warehouse digital twin, we could then say, how do we now communicate with the distributors? How can we improve the efficiency of transport? And then lastly, how do we bring these different assets to the customers in a timely way? So the exciting thing here is if we had all these like multiple digital twins, ultimately these could communicate with each other and we could build an integrated supply chain. So this is one of the big challenges pretty much most sectors have, where supply chains are not integrated, which leads to inefficiencies, and it leads to assets maybe costing more to produce, or there are delays in the production processes. So digital twins could have a big role in creating these integrations. Decarbonization. So this is a project we're currently working on as well. So this is about transport. So how do we, for example, reach 2050 target around net zero? So we're using digital twins to facilitate the transition into net zero. So the project we're working on is called Transit. And in this process, the digital twins are designed in a way that we've got the physical space captured. It includes things like roads, could be a truck, could be an airplane. We're looking at different types of equipment that we're using, like a forklift. It could be an infrastructure like a road, and it could be a facility like an airport. So the physical level, we're seeing how we can collect that data. And then we have the network layer, which is about how do we collect the data, how do we build the control measures, and then in the virtual space, we're trying to optimize across different kind of factors. So the kinds of things we're looking at is the transition duration. How long will it take us to get to net zero? What are the constraints? How do we visualize content so people can make good decisions? And how are we actually going to use the data that has been collected? So there's elements around AI, there's elements around simulation methods, there's questions around how do we get to real-time analytics. So all of these are covered in the virtual space. And ultimately, a key outcome for us is the digital twin is giving feedback to the transport system, and it's breaking it down based on different types of stakeholders. So if I'm a truck driver, for example, I could get some guidance in terms of the route. I could get some guidance also in terms of where can I transport things, in what sort of order, so that I'm optimizing what I'm carrying in that process. So lots of decisions, lots of critical sort of questions there. And digital twinning helps us really to understand this system, I would say this complex system better, and also helps to interact and engage with the system. So I think this slide is really just trying to say, when you're thinking of where can you use digital twins in the future, how do you start to build a bit of a logic in terms of the benefits that you can get from digital twins? So in this slide, there's 3 dimensions that you need to think about. The first one is really saying the application depth. And what that means is it's questioning what type of decision are you trying to make? Is it operational? Is it tactical? Is it strategic? How do you start to characterize the nature of the decisions, the nature of the assets utilization? The second question is saying, what's the application life stage? Like, is this in the concept phase? Is it assessment? Is it demonstration? Is it manufacturing, in service, or disposal? In each of these phases, there's a different type of digital twin requirement that you could have. And then the third dimension is application scale. So that's saying, is this conceptual level? Is it at a component level, subsystem? Could be system of system, or it could be a more wider federated architecture. So, so each of these boxes that you can see in this cube could represent a type of digital twin that you're interested in. And, for me, the key thing here is you've got to specify the requirements. Once you know the requirements, and you can use this as a bit of a structure to decide what your requirements for the digital twin are. So this structure helps to specify what do you want the digital twin to do for you. I think moving forward, the huge opportunities for digital twins will be particularly where it's a complex system. It's a system where there's lots of elements that are interacting with each other, and it's hard to manage any individual part because it's so connected. And I think the digital twins will play a huge role in those environments because you'll be able to start to see how one decision in one area can affect multiple others. So very, very critical to think about future research for digital twins. I think, we're going to be moving more and more towards federated architectures, and we're going to see much more integration across the life cycle. And I think digital twins will play a big role in terms of the process for integrating these different perspectives. So just to highlight some conclusions, there are many opportunities with digital twins. I think, we need to understand what sort of characteristics digital twins have. They offer being responsive. They offer being interconnected. They could help with removing silos in terms of different systems, potentially across the life cycle. We could, by having a common, maybe data architecture or common interoperability approach, you can start to remove silos and improve the confidence in terms of how you represent a system. Predictive is also an opportunity in the sense of by having a better understanding of the system, you should be able to improve your predictiveness and as an outcome, you can improve the performance and optimization of the physical system that you're interested in. So there are many opportunities, and I think moving forward, we need the digital twins to find the right use cases and to demonstrate that they actually can add value and make some significant improvements in the systems that they represent. So with that, thank you very much. And I'll be happy to answer any questions or any comments.
Thank you very much, John, for this presentation. So thank you for sharing your thoughts, your research, and also opportunities and other research directions regarding digital twins and digital twins technologies. Mm-hmm. So I think that in the audience, colleagues and your researchers will be very interested by this, and maybe they will ask some questions. So some other questions from the audience. So I don't know to use the micro or you hear us clearly or? Yeah, can you hear me from here?
We can see you also if you go there.
Maybe not.
You can even see.
Maybe I can get closer to the mic. Can you maybe hear me now or see me?
I can hear you and I can see you.
Okay, perfect. Thank you very much for your presentation, Professor. It was a nice talk and very rich.
Thank you. Thank you.
I have so many questions, but I will stick with one or two. I was wondering have you worked on which we consider important topics for us as well in the ongoing research projects. That are topics around the interoperability, cybersecurity by design, and as well the, let's say, the unified representation or standardized representation of digital twins.
Yes.
So have you worked on this as well?
Yes,
Or maybe
absolutely.
your
No,
future
this
works,
is,
if you can maybe give us more information about that.
So for us, this is a fundamental topic for digital twins to work. If we can't sort the interoperability challenges, digital twins will be ad hoc. It won't be kind of continuous and spreading across, let's say, that federated context that I mentioned. So we are doing quite a lot of work around interoperability. We're typically using ontologies, and we're trying to look at different types of interoperability challenges like data, software, language, and we're trying to see how we can connect different systems based on different characteristics. So very much of interest, and we'd be keen to collaborate on that topic.
Thank you very much for your answer. Second and last question for me. I have a question regarding the work that you have presented on page 12, if I remember well. It was about the resilience of a digital twin and the difference that you added to the system. Yeah. So my question is, are you running these simulations on the real time with the real system, and since you identify the disruption, you run simulations, or maybe you just pick the outcomes of the best simulation outcome, you try to apply it to the physical world, or maybe you just run the simulation from the point of the disruption and then wait until you get the best scenario and try to apply those best outcomes of the simulations to the physical system.
So in this example, we're pretty much near to real time. Now, I think I can say that in this example, the system was relatively simple. Like the range of optimization scenarios that we had were limited. Because if one leg stops working, we've only got a few other legs to modify. So the optimization was not too complex. So because of that, we were able to get to close to real-time simulation. Now, beyond this kind of context, maybe real-time isn't realistic. So I think, I take your point. Maybe there may be some delay in terms of coming up with the optimization and then giving that feedback. It's possible. I agree. But in this context, we targeted to be close to real time, and we are pretty much close to real time. Thank you. Really good questions. Thank you.
So, other questions, and also from remote colleagues or those that are connected through the Teams, so I cannot see the screen. Other questions? Yes, there is one question from Mr. Milan.
Yes, thank you, Professor, for your great presentation. I had a question concerning the models that you have used. For example, I'm wondering if you have used some physics-informed neural networks or something like that, because you're working with physical phenomena. I'm wondering if it's why a first question, so I continue after.
It varies. Yes. In some cases, we've used physics-based, some cases data-based, some cases we've combined them. In some environments, we've said we've got rich data. In some cases, we said we didn't have good data. So absolutely, I think what we're trying to do here is represent the scenarios that industry has. So yes, yes to all the above that you mentioned.
Thank you. Second question is, how do you see the impact of the generative AI for digital twins? If there are already some work that have been done for that, or?
Yeah, I think there's a very nice link between generative AI and digital twins, in the sense that when we're trying to create feedback mechanisms, we need some maybe ability to learn, because we may not have the scenario experienced before. So we need some kind of maybe suggestions, some kind of optimization. So I think there's a huge opportunity with using generative AI. And in literature, there are papers that are being published looking at using generative AI in digital twins. I think, in terms of creating content, in terms of trying to optimize the scenarios, there's huge opportunities there in terms of how we can use the data. But for me, another key thing we need there is generative AI will improve as we have the digital twins working over time. So the ability to improve the accuracy, the prediction capability will improve as the digital twins are in use. Thank you.
Take another question. So someone raised his hand. When you're muted.
Yeah. Hello. So first, thank you for this presentation. It was very clear and interesting. So I have like a quick question in the same direction of the first question of Milad. So I'd like to raise like about hybrid modeling between physics-based and data-driven approaches. And I'm a little bit curious about the nature of their integration. That means, is this a challenge about orchestrating different digital twins? That means each one will handle different model, or is just like hybridization that happen at the level of representation within a single unified model?
I think the answer to this is in terms of how do you design interoperability into your digital twin? Because if you look at the physics-based approach or the data-based approach, there's particular types of software you'll use. There's particular types of language you'll use. Different places you'll store the data. If you want to create that hybrid approach, you need, by design, you need to be able to connect these different types of data. Because if you've got a fixed manual integration, the ability to adapt the digital twin over time will be limited. So a system representation, you need to look at that as a dynamic construct. So that can change over time, it can evolve over time. And I think having physics and data, being able to like have a hybrid approach will enrich the way you're representing the system where possible. So I think the question there is, you've got to think about that design, interoperability design, so that it's possible. Otherwise, it will not work. It just won't be possible to sustain that over time.
Okay, thank you.
Thank you.
Thank you. We have another question from IJ.
Yes.
Yes. So we can't hear you. It seems that there is some problems with the mic. Anyway, maybe the problem will be solved soon. So I've seen the audience if there are questions or remarks. If not, I have one question regarding the accuracy of twin, and specifically when it comes to federated digital twins. So, do you have some ideas about how to define this accuracy? Is it a kind of multi-dimensional, because you have twinning, you have the maturity, you have maybe different aspects? So do we need to think about some measure of the accuracy which is having multiple dimensions?
Yeah. Thank you, Nabil. I think measuring the accuracy of digital twins is key. We are looking at that. And, in some examples, we've reached like 90% or more accuracy, but I think the interesting thing is the accuracy is dynamic. It's not continuous. It can change, and like some examples we've seen, the accuracy can drastically decrease very quickly. So, I think also it is like a multifactored way to look at accuracy. How we've been looking at it is in terms of two things. One, have we represented the system correctly? So that's one measure of accuracy. The second measure of accuracy for us is in terms of if, for example, we've come up with some kind of optimization where we're giving feedback into the physical asset. Has the feedback actually been implemented in the physical asset? That's another accuracy that we define. So I think I agree with you that it's multiple factors that we need to consider when we're measuring accuracy. Have we done enough on measuring accuracy? I think we need more, particularly in the federated context, because the complexity of measuring how well the federated system is working, we need a lot more research in that.
Yeah, so I was trying just to see if there is some parallel between the conformance or conformity assessment when you are in a complex system. So it's quite difficult to define this conformity, but you measure it through each single part of the system. Yeah. So it's a kind of conformity assessment from the single elements, and that enables you to have an overview of the whole system. So maybe this could be maybe a...
So it's very interesting, very interesting. But the challenge there is, in a federated context, each of those elements are connecting to each other. So if you make one change in one, let's say, in the example I gave, mobile car, if you make one change, it has a knock-on effect. So that knock-on effect can change the accuracy.
Questions? I have one regarding the actual research on digital twins in UK. Yep. So is it because you have shown a lot of applications for decarbonization, for the supply chain? I think that in UK there is also some important projects about buildings, about the city, about the territory. So today, in your opinion, what are the most important applications today in digital twins beyond manufacturing?
Okay. I mean, I tend to work in manufacturing, so I think my sort of observations, we've seen some examples in like fashion industry. I've seen interest also in tourism. I've seen interest around construction. There's a lot of interest around construction, and also in the likes of defense sector. So I would say there's a lot of interest across a lot of sectors, but in terms of who is actually using this or implementing this, manufacturing, aerospace, defense, they're the types of, maybe rail as well, they're the types of sectors that are maybe more advanced in utilizing the concept.
Thank you. Questions? I have one which is related to education. And I think that you are active in, you have a master program on digital twin. So what's the actual experience? What are the needs, the actual needs regarding a new curricula or adapting curricula that integrate digital twins for both academia and also for companies that also are looking, I think, to have new skills and new knowledge about digital twins.
So I think I'll just mention the two experiences I'm involved in. One is a short course that we have. It's called Digital Twins for Senior Leaders. So that's very much about trying to understand the use cases for digital twins and how we can design these so that companies benefit from these. And the second one is a master's course where we're very much focusing on digitalization and digital twins, I think for me, what kind of skills needs are very much the whole journey. How do we take an integrated approach? Because just trying to have good quality data is not enough. Just trying to have good analytics is not enough. How we connect data to models, to visualization, how we have each of these things at a good level. You need to think of this in a holistic way. And I think that's what's different. Because if we look at traditional education, we focused a lot on maybe sensing, or we've focused on good modeling methods. But the difference here is we need all of these things. We need these to connect. We need these things to kind of work in a seamless way and to provide that feedback back into the physical system. And we haven't done these things before. And to me, it's a significant change in the way we manage assets. So yeah, it's very exciting in terms of education and skills development, because I think if we get this right, the impact in industry could be significant.
Okay, so no other questions. So I would like to thank you again, John, for this nice and very important presentation. I think that gives a lot of insights, and it goes on deep also on some main concept of digital twin. Thank you very much.